Alright, so let's continue working on our PMC routing, and last time in our previous lesson we stopped at trying out this precise classifier of OpenCascade implemented in BRep class 3D solid classifier, and what we saw is that this classifier takes sometimes forever to converge, and that's not an option in any realistic industrial application, of course, unless what you are doing is just testing out a single point if it belongs to a solid or falls inside your solid or happens to reside on the boundary of your solid. So that's definitely not what we want to have, because the performance of this solution is not satisfactory, and let's see if we can do something better. And last time I also presented you this classify PT tool. It's a header only tool. You can find it in the lesson repository. It's quite a sophisticated thing, but the principle behind it is very simple. So what we do here, we build initially like a triangulation out of our geometry for our solid. We have this triangulation, and after that we build bounding volume hierarchy so that our shape is represented with a hierarchy of nested axis aligned bounding boxes. And then, having this hierarchy, we can implement very efficient classification procedure. Like whenever we want to test a single point, we first identify the ultimate box in the hierarchy this point belongs to, and once we know the box, we know also the series of triangles captured by this box, and we can narrow down the whole check to the check on this small number of triangles. That's why it's quite efficient. Let's give it a try here, and to give it a try, of course, we need to have this triangulation first, and so far we have only this shape. So the initial step would be to build triangulation out of our precise shape. As you might probably know, especially if you've been watching the videos on this channel, to build the triangulation out of your geometry, you can use this BRep mesh, incremental mesh tool of OpenCascade, which we normally call a faceter. So it's a faceter, it gives you this visualization quality triangulation. It's not good enough to be used in any engineering simulation, so to say, but it is perfectly fine for visualizing on a display, like using your graphics card, because here you have very small, like a minimal number of triangles. If you have a box shape, you literally have just 12 triangles to represent it, because each side of the box will be represented by exactly 2 triangles. So it's very compact and efficient. And we have it here, and now what we want to do, we want to collect all the triangles in a single group, so that we have this polytriangulation data structure that can be then passed for visualization into our viewer. So let's have it here, and to collect this triangulation we need to start from iterating all the faces of our geometry, because this triangulation, these facets, they reside in the individual faces of our geometry. So for that, let's go and run iterator. So we have this explorer right now, and we use this explorer to iterate our shape by faces in this context, but we can also have used it for iterating our shape by edges, vertices, and whatever subshape type you might want to have here. So let's take a face. It's going to be topodias face, and it's a const reference that I can take from my current position of the explorer, and I only need to downcast it to the shape type, because this explorer, it returns the base type, which is topodias shape, and I need to have this face out of it. So we have this face, and now we can extract polytriangulation out of it. This is a series of triangles associated with a single face. So let's do that. For that, I'm taking this BRep tool, then triangulation, and then face. You can also see that here we are supposed to pass an instance of top lock location. That's necessary because even in the scope of one model in one solid, you can have different locations for your shape, for your faces. And this location is essentially like a transformation matrix, and it will be returned as an output argument. So I'm going to pass here top lock underscore location. We pass it here, and as a result of this invocation, we are having this handle to poly triangulation object trees. Or we can name it like face trees to emphasize that this triangulation is associated with a single face we have. Alright, so we have it here. And what I want to do actually is I want to compose a single bulk of facets, like just one triangulation object, because here it's not quite what I want to have, because here you can see it's an iterator, and I'll have as many triangulation objects as many faces I have. That's not what I want. I want to have just one triangulation. That's why I'm going to allocate a different object here, like trees. And here, if you check what you are supposed to pass in the constructor of this object, of this class, you'll see that you are supposed to pass there the number of nodes and the number of triangles, which you are supposed to know. But the problem here is that you have no idea basically how many nodes and triangles you are having in your shape after you run this BRep mesh, and basically it will be more convenient if I can dynamically allocate the memory as long as I add new elements to my triangulation. So it's not the collection which I want to use, and instead of it I'm going to use a different class, also coming from OpenCascade, also from the poly package of OpenCascade, but its name is coherent triangulation. This coherent triangulation is a bit more handy in the sense that it allows you not to care that much about how many triangles and nodes you are going to have in your triangulation, and also it's quite computationally handy as well, because it gives you all the necessary, iterators. Like you can also have, you can run an iterator around a single node or triangle, like to circulate around a single element. And this data structure allows for more local working with your mesh data structure. So if you are looking for some efficient surface triangulation data structure, you can definitely take a look at this coherent triangulation, because it's quite efficient and quite useful in the algorithms. But here I am going to use it only because I want to have like a dynamic collection there. I do not care about how many nodes and triangles I have in my triangulation. So I just go and allocate this coherent triangulation from the heap memory, like this. And then let's see how am I supposed to populate this triangulation. We can find that I have like add triangle method here, and also I think there should be like a set node or something like that. Yeah, you see that there is a set node method that accepts like a triplet of coordinates, and also I have this add triangle method in here. So basically, if I want to add a triangle to my coherent triangulation, I need to take it out from my simple triangulation associated with a single face. To do that, I take my face trees, and there is a method called triangle, and basically it accepts an index, which is a one-based index of a triangle inside my face. So it's not like a global index, it's a local index inside a face. So to use this method properly, I need to run a nested loop. There I'll iterate over my triangles inside a single face. So here I have this I_try counter, and it will go from 1 till the number of triangles in my local triangulation. It's number triangles here, yeah. And then I increment my counter, and finally I can access it like this. So I have a triangle here, and this triangle is returning to me this const reference to polytriangle. So let's get it from here. In OpenCascade, whichever triangulation data structure I take, would it be like coherent triangulation or simply triangulation? A triangle is a series of indices. It's just a triplet of integer values pointing to the corresponding nodes and the nodes are stored in a different array inside my triangulation. So the only difference in that sense between polytriangulation and polycoherent triangulation is that in polytriangulation we have fixed size arrays for our nodes and triangles, while in the coherent triangulation we have dynamic vectors for the same data. Like we have one dynamic vector for nodes and another vector for triangles. What it means is that I can now access, using the get method of my triangle, these three indices of the nodes. So I can take them out. nodes, I'll have this fixed size array of nodes, and I'll pass them the elements of this array as output arguments to my get method in here. So here we have this array for triangles and we are accessing these nodes, but the problem here is that these nodes, they exist in my local triangulation of the face, but they do not exist yet in my target triangulation, my target coherent triangulation. So I want to do a different loop here and add all these nodes to my coherent triangulation first. So I'm going to run it like this: int I node also starting from 1 and goes until face trees nb nodes, then plus plus I node. There we go, and here I can access my node by its index using this face trees node, I node as an index, and now I can add this point to my coherent triangulation. For that I use coh trees set node and then pass there with p. So this way I add all my nodes, and now I need to match those node IDs here to the node IDs of my coherent triangulation. So I need to have some mapping, and here I'm going just to use a map. It can be like an ordered map because order doesn't matter. So I want to have a map between a local node ID to global node ID. So this way I keep track of my node indices. Nodes map. So now I want to insert to this map a tuple or a pair of indices, and the first index is my local index of the node, which is simply I node, which is 1 based, and in coherent triangulation it's different indexation of nodes. So the indexation in the coherent triangulation is different because first of all it's not 1 based anymore, it's 0 based, and also it's like continuous indexation. It has continuous indexation, meaning that for the second phase it's not going to start from 1 anymore or from 0. It will continue incrementally increasing its indexation in this collection. So here I need to pass this coh node index. And now I have this mapping, and I can take advantage of this map right here because I now can take out for this local node index its global counterpart in my coherent triangulation. So I can create like a new array of nodes, coherent nodes, and initialize it from this map as simple as that. Alright, and now okay, I have this global node IDs. Now actually I'm supposed to use square brackets here. because it's a standard collection, like an STL collection. If it was like an OpenCascade collection, I would use these round brackets instead. And now, having these global node indices, I can add to my coherent triangulation a new triangle based on these newly added nodes. So as a result of this code here, as a result of this for loop, I'm going to have this single piece of triangulation collected out of the elementary triangulations taken out from the CAD faces I have. But it's coherent triangulation, and I want to convert it to the more traditional poly triangulation. To do that, I can simply take these coh trees and run its, invoke its get triangulation method. So as you can see in OpenCascade, sometimes a getter has this get prefix and sometimes it does not. Alright, so let's have this handle poly triangulation, and I'll name it just trees. And now I can use my vout visual stream and pass there my triangulation like this. Alright, so now I want to make sure that I'm in the release mode. Yes, I am. Now I have this solid classifier, which, if you remember, was quite a heavy thing. And what else do we have here? We have this vout shape, but it's commented out, so that basically means that I'm expecting to see all the points inside my shape and also to see this triangulation which I just constructed. So let's have a look at it. Let me compile this whole thing and run it. I would expect it to take a bit of time for the classification by the OpenCascade tool. And other than that, the triangulation should be here. Alright. So basically we can see some visual artifacts here. As you can see, something is strange with the colors, first of all, because, I mean, just to explain, this visualization of triangulation here in this exercise is quite advanced, in the sense that it highlights out of the box different anomalies in your triangulation. And what you can see from these two distinct colors is that some faces are kind of flipped, and there is something wrong with the orientation field in your model. And basically that happens because whenever I took this triangle from my face triangulation here, I did not quite take into account the orientation of the face, because the face itself might happen to be reversed. And if it's reversed, then I'm supposed to kind of change the orientation of the corresponding triangle as well. And the easiest way how we can do that is we just check the face orientation right after we extracted already the node indices of our triangle. So we can go for an if statement here and check that what is the orientation of my face, and the face is this variable here in the loop. So if my face is reversed, it means that its orientation equals top ABS reversed. Then let's swap these indices of our triangle. Basically what I have to do, I have to go and std swap some of those indices, so I can swap just I nodes 1 and 2. So if the face orientation is forward, then I have indices like 1, 2, 3 in that order. But if it's reversed, then I'm going to have them as 1, 3 and 2. And if you think about it, you will shortly realize that it has something to do with the vector product of the corresponding vectors. So if I change these vectors, then I'm going to have like a flipped vector product out of them. So let's give it another run. You see that this is the initial state of my geometry, and if I change this code taking into account my face orientation, it's going to be a bit different. And now we see that the entire model is now brown, and it means that this kind of an issue with flipped orientation now disappeared. But we also see that there are some other problems with this model. Basically, some faces are not right in place. We see some faces visualized here, while you can shortly identify that their true position is here, basically. And another problem with this model, also here you can see that this is like a bottom face for all these holes. All these holes in this circular pattern are missing their bottom face, because this is just a single face shared as many times as many hole occurrences we have here. This is quite funny, and we need to fix it as well. And you can also see these white balls. And these white balls indicate that the corresponding vertex here is not shared. It means that it's a sort of like a duplicated point that is supposed to be shared, but it's not shared. And to fix it, fixing it is a bit more tedious, is a bit more laborious, and we're not going to waste time on it. Actually, if you want, you can check the corresponding functionality in Analysis Situs, or we can discuss it on the forum, where this sort of code is more sophisticated, and it can also handle these repetitions of coincident nodes. Instead of fixing that, we would rather fix these displayed faces. And here, if you remember, when we extracted the triangulation of our face for the first time, we also passed there this location, which is basically like a transformation matrix. And now we want to take advantage of this transformation matrix, and when we extract the point from here for the first time, we can also transform it accordingly, like we return the transformed copy of the node using this transformation matrix. So this is a situation initially. We have these strange faces here and over here, and we have those gaps. Now if I apply this simple modification, like I transform my coordinates with respect to the transformation matrix which I've got from the face itself, then it's going to change the whole appearance of my model. Let's wait for the classification to finish, and you see that now it's much better. We do not have those gaps anymore, and also those faces are fixed. And for those three nodes, let's forget about them actually. And if you want to fix them, then post a comment, or I welcome you to the forum where we can discuss how to fix it easily. Now we have this triangulation, and now we have everything to run this classification tool. So to do that, we are going to use the same sort of a loop like here. I just copy this loop from here down below. Now instead of having this classifier, I'm going to allocate, I'm going to create a new tool which is classify PT. It's a discrete classifier. Now we iterate over all the points in our grid, and we apply the same classification logic. Like instead of running this perform, we can just ask if the point is inside our solid. We are also going to keep here this precision confusion, and to remind you, this precision confusion, this second argument here in the classifier means the tolerance near the boundary for a point to be considered as belonging to the boundary, like not inside or outside, or rather as belonging to the boundary. So, and if this classifier returns true on its isIn method, then basically we can just go and output this point to the output stream. And now what I want to do, I want to comment this line out so that we do not mess up with the previous classification results, and we will rather keep only these classification results from the discrete classifier. So let's compile it again and see what's going to happen. Okay, so the old classifier is still alive, and that's why it takes some CPU cycles to converge. And now the second classifier also runs. You see that there are some points in here. I think it can be interesting to disable the visualization of the meshes, but you can already see that this classifier, the second classifier, is 100 times faster than the OpenCascade's one. So let's just, to sum it up, let's just remove this visualization from here so that we can see only the points inside the shape. So these are the points. And this classifier again is very, very fast. And what I can say that in our projects, the projects conducted by our team, we are using all the time almost exclusively the second classifier based on VVH, because the first one is terribly slow. Although it's precise, while the second one is based on the discrete representation of your shape, and it's not that precise, and you have to be careful about the discretization error of the boundary itself when you run it. But in most cases, in the engineering cases, you have some, engineering tolerance that says how inaccurate your geometry could be, and you can use this tolerance for the classification routing. So that's basically it. That's what I wanted to cover in these couple of lessons related to point membership classification. Again, this point membership classification is a fundamental thing in any, geometric modeling system, and it's not only theoretical. It's anything but pure academic question, because in your projects, in your code, it's very often when you need to do this sort of computation, and you need to know that you're not obliged to use the tools that come from OpenCascade itself. You can always add some more tools into the basket, and you can have your own set of very optimized, efficient tools that would work together with OpenCascade to do the job. So I hope you found this lesson interesting, and see you next time in the following lessons.